Hi, and welcome back. A couple more derivations. So in chapter 3, Kuchemann will talk about a pressure coefficient, and that coefficient is just P minus the static pressure normalized by dynamic pressure, 1/2 rho 0 v 0 squared. And so he then drops in these things that look like this kind of nightmarish form. And so I want to walk through this, and then there's one other relation that'll become super useful for us from an ideal gas high-speed flow point of view. Okay, so the first one is looking at this gamma rho v0. Really, you can, the bottom part, you can split this out and say this is the speed of sound. I'll use A0, just so C's are already kind of used here. So A0 Mach 0 squared. Okay, and then remember that the speed of sound A0 squared was equal to gamma P over rho. And so then this term is actually just 1/2 gamma P0 Mach 0 squared, which coming back up will then turn this term, and I got that P0, which kind of cancels things out. We'll have 1/2 gamma Mach 0 squared, and then we'll end up having P over P0 minus 1. Okay? Gosh, that got a little high. This is a P. It's P. You can see it or not. Fine, I'll rewrite it down here. 1/2 gamma Mach 0 P over P0 minus 1. Okay, so we'll come back to this. Gosh, even that was pretty not neat. 1/2 gamma Mach 0. Yeah, we'll be fine. Okay, so one more relation before we put that in a different form, because the Kuchemann just kind of drops this like really gross expanded one. So I'll come back to my notes and kind of walk you through that each step, and because there's a lot of Taylor series expansion that gets in there. So it's super useful. So I want to come back to our Bernoulli for a second. So we derived that last time, v squared over 2, and then it was gamma over gamma minus 1 P over rho is equal to constant. Okay, so I want to do a little bit more work here. Okay, the first one is just like before. This is A0 squared, right? I have a 0. This is Mach squared, speed of sound squared over 2. Okay. Gamma over gamma minus 1, P over rho is equal to constant. Okay. And then now I'm going to put A squared, I'm going to put the pressure in. Okay. So that is this term over here. And so that gives me gamma P over rho over 2 rho Mach squared plus gamma over gamma minus 1 P over rho is constant. All right, well, gamma is just a constant. So if I divide both sides by the gamma, this is still just a constant. The constants change, but it doesn't matter. Right? So I know I can get rid of the gammas. Okay? And then I'm going to gather the terms. One more move here. Yeah, I'm going to gather the terms. And so then that's P over rho. I have a Mach squared over 2 plus 1 over gamma minus 1 is equal to constant. Okay? And then, again, just like I did last time, gamma minus 1 is also constant. So I'm going to multiply through also by gamma minus 1. And then you end up having sort of the more familiar form of this, and I'm going to swap these two, such this is then 1 plus gamma minus 1 over 2 Mach squared is equal to constant. Okay, so that's a form that we end up seeing quite a bit. Okay, quite a bit. In fact, you can even come back and and take a look at how that's basically just temperature. So one more form on this. Okay, so this is pretty damn useful. Remember, this is just the Bernoulli equation. I haven't even done anything yet from there. So now if we then say this is isentropic, where, as I remember, that's P over rho to the gamma is also equal to some constant. Okay. Then again, if I call this, I'm going to call this constant C1, or actually I'm going to call it C2. That will then give me rho is equal to P over whatever that constant is to the 1 over gamma. Okay? And so this constant, remember it's true for any Mach number, m. And so I'm actually going to say that when Mach equals 0, that's going to be our total state. And so that means that this whole thing is actually equal to P total over rho total, right? So basically, if Mach is 0, this term vanishes, and it's just whatever that pressure and density is. So that's our total term, okay? And so then putting in what P over rho total is, then rearranging, I'm now going to bring this term up. So put a line here. This is 1 plus gamma minus 1 over 2 Mach squared is equal to P total over rho, over P total over P, this term, and then rho over rho total. Okay? But remember here, this rho over rho total is just the same as, make sure I get this right, that's a P total, this rho comes in, and so that's another P total P over P, and that's a 1 over gamma. This is a minus. Okay? And so then that is just P total over P. So combining that, that's 1 minus 1 over gamma. Or the usual form, you write that P over P, gamma minus 1 over gamma. Okay. So I'm going to write that down one more time here. PT over P is equal to 1 plus gamma minus 1 over 2 Mach squared gamma minus 1. All right, so that's the ratios of pressure. And then if you actually go back and you push this back in for temperature, and that's really how we'll end up using this form a lot in terms of temperature. Okay. 1 plus Mach squared. Right. And so we'll end up seeing this one a lot, especially when we talk about airflow coming in and kind of compressing and what's the temperature ratios. So we'll come back to that one for sure, but this one we use a lot. All right, so now we have a relationship between P and P0. And so the final stuff gets a little messy over here. Hopefully I have enough room to write it. So this equation then became 1 over 2 gamma Mach squared. The ratio of pressures is then really 1 plus gamma minus 1 over 2, and that's Mach 0 squared because it's opposite, right? This is a P total over P, and this is 1 plus gamma minus 1 over 2 of whatever that actual Mach is, squared, and that gets raised to the gamma over gamma minus 1, and then subtract 1. Okay, so this is the pressure coefficient so far, and now we've at least gotten it in terms of the kind of the free stream Mach number and the current Mach number. And so if this is the coefficient of pressure over a wing, then basically it's saying as long as we can get the pressure coefficient as long as we know the Mach number around the wing. Right, so that's already pretty useful. Okay, and then furthermore, what we're now going to say is if 1 is far greater than gamma minus 1 over 2 Mach squared. So, you know, if it's compressible but kind of small, then we can actually expand this term, right? This is the Taylor series expansion. And so if you haven't seen Taylor series expansion before, up here, if I have a term over 1, say minus epsilon for small, that's basically the same as 1 plus epsilon, as long as it's small, plus things that are order of epsilon squared, which would be really small. And so what that lets us do is then take this term and switch it out, okay? And so we then have 1 over 2 gamma Mach squared, and that is 1 plus gamma minus 1 over 2, there's Mach 0 squared, and then multiplying it 1 minus gamma minus 1 over 2 Mach squared. All of that is still raised to the gamma over gamma minus 1 minus 1. Okay, and so then multiplying through, that is then 1 over 2 gamma Mach squared. Multiplying through, I have 1. We then pick up a minus plus gamma minus 1 over 2. So the higher order terms cancel. And this is then just Mach 0 squared plus Mach minus Mach. It's a minus sign there. Minus Mach squared plus higher order terms that aren't going to matter. I still need another bracket here because that's still raised to gamma over gamma minus 1 minus 1. All right, give myself a bit more room. Okay, and then we're gonna say that, remember that Mach over Mach 0 is the same as a, right, speed of sound times v over a naught. Let's see. Speed Mach number is a over v, so that's 0 goes up here. V0, A0. Here we go. Okay, and then so this term Mach squared, this whole term, I'm going to pull out a Mach 0 squared such that we have 1 over 2 gamma Mach 0 squared, bracket, still in the bracket. That's a 1 plus gamma 1 is 2. I've pulled out a Mach 0 squared, and that's going to give a 1 minus basically v over v naught squared, and that is all of that raised to the gamma over gamma minus 1, where we've now made the further approximation that a is pretty damn close to a naught, because we already had this term that said we're compressible but we're low speed. That was this term right here, compressible but low speed. Okay, so this is then finally the term that Kuchemann drops in chapter 3. It just this one-liner statement that says, hey, the coefficient of pressure is this. So as nasty as that was, I'm going to circle this thing, and then we're done for this episode. Okay, so this is the coefficient of pressure, and because then he will then walk through an expansion once we know if we have a velocity field that we'll get from inviscid flow theory over the wing. He'll then drop that, and this will then have a really simplifying form, sort of under this linear inviscid format, but he just kind of dropped this out of the sky. So I wanted to myself walk through this, was many pages of math to figure out how to get to this point. And again, the thing that Kuchemann didn't drop in there, and that's why it was important for me to redo it, was this whole assumption was already baked in two things. The first one was just that it was this term is pretty small, so it's still compressible, but we would say it's kind of small. Mach squared is small, gamma minus 1 over 2. And we would usually say that's, if you've ever heard that incompressible, if you will, if you've ever heard that it's, sort of incompressible as long as the Mach number is less than 0.3, it's because of terms like this. So if you squared 0.3, what you end up getting is that this is 0.09. And then if you multiply it by, the number, it's basically saying that this number is a 5% correction. And so that's not too bad. So if this is a 5% correction, then the expansion up here is even tinier. So that's usually what this means. Okay, we'll see you next time. We've got one more, not nearly as bad page of derivations, and then we'll be ready to kick into chapter 3.